Matter, that's going to be the topic in this very first lesson of my brand new general chemistry playlist. And it's an appropriate topic because chemistry, simply put, is the study of matter. And we're going to learn a lot of vocabulary of how we look at matter and how we classify matter and how we measure matter in this first lesson. Now, before we dive in, I really just want to give you a proper introduction to the entire playlist. This general chemistry playlist is going to span 2 semesters of college general chemistry. That's General Chemistry 1 and General Chemistry 2. And we're going to present this in roughly 90 lessons, give or take, spanning about 20 chapters of general chemistry. It is meant to be thorough and comprehensive to just about anything you'd see in your typical college general chemistry course. Now, I also want to make you aware of one other way that you can consume this course, and that is on my website at chadsprep.com. In fact, all of my playlists, including a couple that I don't even have here on YouTube, are embedded as course playlists on chadsprep.com. And they've got nice collapsible menus that kind of show the breakdown of chapters and stuff, and it's just a little easier way to navigate through the course playlist. Now, I've got the old general chemistry playlist currently embedded there, but as I release the new lessons, I will be replacing them with these. But as it stands, there's the entire Gen Chem playlist already there. Just be updated as we go throughout the school year. And finally, I just want to make you aware of my premium courses. Like I've got a General Chemistry Master course, which on top of the video instruction also includes about 75 pages in study guides, as well as 1,200 plus practice questions. It also includes a final exam rapid review for both first and second semester, as well as practice final exams. So if you're not familiar with this fact already, your typical science class, the majority of your real mastery of the material is going to occur when you're working practice problems, not while you're watching a lecture, however good or bad the quality is. Now, in addition to having master courses for many of your high school and college science courses, we also have DAT, MCAT, and OAT prep as well. Just an FYI. All right, I've been yammering on enough here, so let's dive in and let's have a little discussion about matter. So what is matter? So simply put, matter is anything that has mass and occupies space. So it has mass and it has volume, would be another way of stating it. So that's what matter is, simply put. And what you want to know, though, is that matter is made up of these super teeny tiny particles that we call atoms. So, and we've kind of, built on what some of the ancient Greeks said. They were atomists, and they believed in these atoms being these tiny building blocks. Well, our conception of what an atom now is a little bit different than theirs, but we are using the same word they did. We've been using it for a couple hundred years now, and so, but you should know that matter is made up of atoms, and it turns out there are different types of atoms, and there's roughly 118 different types of atoms, and those different types we call elements. But these 118 or so elements, that's the number of types of different atoms that are out there, and everything in the universe that we can see, so is made up of these atoms of 118 different types. Okay. Now, it turns out this matter comes in 3 major phases or 3 major states, and we're going to call those solid, liquid, and gas. And you might be like, oh, Chad, what about plasma? Well, you're right. There is a 4th phase called plasma, and we're not talking about it. So you're not going to see it in this class. We'll have a whole chapter dedicated to talking about solids and liquids toward the end of the first semester topics. We'll have a whole chapter talking about gases. We will not have a whole chapter talking about plasma, and so we're not really going to include it. But you should be intimately familiar with solids, liquids, and gases, but only marginally familiar now. But once we get there later in the semester, you'll learn a lot more about all 3 phases. So what you should know, though, is that solids have a definite shape and a definite volume. So both definite shape and definite volume. Whereas a liquid, when you pour it into a container, it just takes the same shape as the container. So it does not have a definite shape, but it does have a definite volume. And then finally, gases. So it turns out gases are going to fill whatever container you put them in. And they will expand to fill that container and stuff like that. Or you can compress them to fit into a smaller container and things of this sort. And so not only do they not have a definite shape like liquids, but they don't even have a definite volume either. And so that's kind of what you should know in this description of solid versus liquid versus gas. Again, solids, definite shape and definite volume. Liquids have only a definite volume but no definite shape, and gases have neither definite volume nor definite shape. And if you kind of look at what these look like at the atomic level, in a solid, what you'll find is that most solids are what we call crystalline solids. And the atoms are kind of arranged in a nice repeating pattern. We call this a crystal structure. And so if you kind of looked at a lovely illustration of what a solid might look like, it might look something like this. And it turns out that these don't actually just have to be individual atoms, but they might very well be, but they could end up being molecules, which are combinations of atoms as well. So That's what a solid would look like. It turns out there's also something called an amorphous solid, which we'll study much later in the semester, where it's actually pretty random where these lovely atoms are. So, but the key is most solids are crystalline, and the idea is that typically these atoms aren't really moving to any significant extent. Now, a liquid's going to be different, so you'll find out that liquid is a little more random. And you'll find out that these atoms are moving around as well. They're flowing, if you will. And so they're not going to be in this crystal lovely structure, and they're not going to be restricted in their motion. They'll be able to move around as compared to a solid. Now, gas is going to be a little bit different because now you're going to find out that these atoms are actually spread out and they're moving. And it turns out they're moving typically faster than the corresponding atoms or molecules in a liquid are moving. So if you're looking at an illustration, you might just have a general idea of how to compare a solid versus a liquid versus a gas. Makes a lovely test question. Cool. Now that we've gone through the 3 phases of matter, we've now got to compare and contrast some new vocab terms that are going to help us to describe some of the properties of matter, as well as kind of some of the classifications of matter as well. Let's dive in. All right, so the first way we're going to classify matter is we're going to compare and contrast elements and compounds. And we've already used that word element. We have this lovely periodic table of the elements. And in this case, all these lovely elements have got their lovely chemical symbol, which we use to represent them. So like sodium is Na and carbon is a C and so on and so forth. If we look at what these elements are, again, this is one of the fundamental types of atoms that exist, is one way to look at that element, but there's another way. So it turns out that a substance that is only made up of one type of atom is also called an element. But then a compound is going to be a substance that is made up of multiple elements. So a good example here of an element might just simply be that sodium. So we got plain old sodium metal, and if you look at sodium metal, it's a solid at room temperature, and every atom in that metal is by and large going to be sodium. Now there's a chance there could be some small amounts of impurities, but I mean, assuming you've got pure sodium metal, every atom would be sodium. On the other hand, you can have sodium chloride, which is salt, aka table salt, the same stuff you put on your food that your mom probably has lying around in your kitchen. And this is a compound because it actually has 2 different types of atoms present in a 1-to-1 ratio. And there's sodium atoms and there are chlorine atoms. Now it's still just a single substance, but this single substance isn't made of just one type of atom. It's made up of 2 types of atoms. Now we've got to be careful on how we look at this, because whether you've got an element or a compound, you're typically, as long as you're not in the gaseous state anyways, you're typically going to have a bunch of atoms bonded to each other. So in pure sodium metal, all the sodiums are in a big chunk in the solid phase, and in some measure they're bonded to each other. Whereas in sodium chloride, you get a repeating crystal, and now you've got all these atoms bonded to each other as well, but now it's not just one type of atom, it's 2 types, and again, in this case, present in a 1-to-1 ratio. So both of these could be used to describe a single substance, but this gets a little bit problematic because now we've used the word element in 2 different ways. We've here used element as one of the components in a compound, and that's totally acceptable. But the other use of the word element is when the element itself is a standalone substance. So like when I have sodium metal. So here I've got the element sodium in a compound, and here I've just got the element sodium itself. And so I just want to make sure you realize there's 2 different, very similar ways we use that word element, but not quite exactly the same. Now it turns out that not all the elements on the periodic table in their elemental form come 1 by 1 by 1 like sodium. So it turns out some of them actually come 2 by 2 by 2. So it turns out like nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen all come 2 by 2 by 2 in their standard what we call elemental form. We refer to these as the diatomics, the 2 atoms, if you will. So, and there's 7 of them, and you should memorize them, and we'll bring this up later on in the semester again, but I figured I'd give you a preview here. So, and what's convenient is that 6 out of the 7 here form the shape of the number 7 on the periodic table itself. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and then hydrogen is the 7th one. Sometimes we'll give you a mnemonic to help you memorize this as well, and we'll say, never have fear of ice cold beer. So either way you memorize it, you're on the hook for memorizing all 7 of these lovely diatomics. And so in their elemental form, they come 2 by 2 by 2, but just keep in mind again, when they're part of a compound, they don't have to come by 2, 2 at a time. They could, they don't have to. So, but this would be elemental chlorine, and this would be, again, non-elemental chlorine, part of a compound, just one component of a compound. All right, so I just want to make that clear a little bit, and elements versus compounds. And now we've got to talk about what happens when you've got more than one substance present. What do we call it there? All right, now we're going to compare and contrast a pure substance versus a mixture. In a pure substance, you've got one substance, but that one substance could be just one element, or it could be just one compound. Either way, we refer to it as being a pure substance. So if I have, say, pure oxygen gas, or just pure sodium metal or something like that. So that's just a single element present. Okay, great. But a pure compound, something like water, so water is made up of 2 elements, but it's still just a single compound, a single substance. And as long as I've got water and no other substance is present, this would be an example of a pure substance as well. So a pure substance is either a pure element or a pure compound. Either one qualifies. Whereas now a mixture is going to be some combination of multiple substances. Now we got to be careful here, because a lot of students will look at this and be like, well, what's the difference between having 2 elements like this or having like air? So air, it turns out, is mostly a mixture of nitrogen and oxygen gases. Well, the difference is this. In water, the hydrogen and oxygen atoms are bonded to each other. So in air, though, air has different components that are together in the mixture, but they're not actually bonded to each other. And that's what makes the difference. It's not a compound, it's actually a mixture instead. Are the atoms bonded together? Yes or no? If they are, then those 2 elements being bonded together forms a compound. So if they're not, then these 2 elements together form a mixture instead. And so air is mostly made up of nitrogen, oxygen, a little bit of carbon dioxide, a little bit of argon, things of this sort. But if you have more than one element that are still separate substances but mixed together, that's a mixture. You could also have multiple compounds, like we could have salt water. And guess what's in salt water? Well, salt and water. And again, salt is NaCl and water is H2O. In this case, again, these don't end up bonded to each other with chemical bonds or anything like that, but they are present together. And because we have multiple substances together, in this case 2 compounds, that once again is going to be a mixture. So you're going to have to be able to distinguish between pure substances and mixtures. And now it turns out we're going to make this even more complicated, because the next level of classifying matter is you're going to have to distinguish between 2 different types of mixtures as well. All right, so the 2 in principle types of mixtures that exist are referred to as homogeneous mixtures and heterogeneous mixtures. And difference are going to be in these prefixes here that will help us memorize the definitions here between homogeneous and heterogeneous. And homo, you might know, means the same, and hetero means different. And so in a homogeneous mixture, what is the same is the composition throughout the mixture. Like if you had a big mixture and you took a little sample here and a little sample there and a little sample there and a little sample there, no matter where you take the sample, it would have exactly the same amount of every component. The composition would be the same, or we use the word uniform. So we often say that the composition is uniform throughout the mixture. Another word for a homogeneous mixture is the word solution as well. And when you think of the word solution, you're typically going to think of a liquid solution, but you can also have solid solutions and gaseous solutions as well. And again, as long as the components are spread out uniformly throughout the entire mixture, so it has uniform composition, then it will be a homogeneous mixture. So a good example of this would be air. If I take a little sample of the air in this room at anywhere in this room, so the likelihood is that there's going to be a set amount or a set percentage of nitrogen, like 78%, as well as oxygen, 21%, as well as a little bit of CO2 and things of this sort throughout the room. That's kind of the way it works. It's got a uniform composition throughout. Now, heterogeneous is an example of a mixture that does not have a not have a uniform composition throughout, doesn't have the same composition throughout. So let's go a little non-chemistry example here first. So in this case, let's go with a salad. So if you look at a salad, typical salad, it's got a lot of different components. It's a mixture in this case. And if you take a bite of that salad, so sometimes you might get some tomato in a bite, sometimes you might get cucumber, sometimes you might not. And depending on where you got that bite, where in the bowl you got that bite, you might get a different set of components in every bite. It does not have a uniform composition throughout. And so a salad would be a great example of a heterogeneous mixture. So a nice supreme pizza would also qualify as well. So in some bites of that supreme pizza, you might get some pepperoni, and some bites you might not. In some bites you might get sausage, some bites you might not. Some bites you might get olives, some bites you might not. The composition is not uniform throughout. Another good example of a heterogeneous mixture. So let's talk about some more chemistry-related examples of this. So, and here's going to be a little bit strange. We're going to put salt water up here, and then we're going to put salt water over here as well. And this is about to get a little confusing. So it turns out salt water could be homogeneous or heterogeneous depending on the situation. So let's say I took a pinch of salt and I dissolved it in water, and it all dissolves. Well, it turns out when it all dissolves, it will spread out uniformly throughout the entire solution, in which case it would be a homogeneous mixture. However, it turns out that salt is only going to be what we call soluble in water. And it turns out if you put too much salt in, not all of it's going to dissolve. And once you get past that certain point, the rest of it is just going to sink to the bottom and sit on the bottom of your glass or your beaker or your flask or whatever you got for a container there. And if you get to that point, well, then you're going to find out that you have a ton of salt just sitting on the bottom, and then you have, lesser amounts dissolved throughout the solution. But depending on if you take a sample right at the bottom or somewhere else, you might get a different concentration of salt, a different composition for the mixture, in which case it would be a heterogeneous mixture. So that's kind of the deal there. Let me give you one more, and we might use something like milk. And milk could be another example of a homogeneous mixture. So up to a point, right? If you leave that milk out on the counter all weekend, then it might curdle. And the parts that are curdled versus the rest, it might actually no longer be homogeneous. But milk itself is homogenized. You might hear that word used. And because it's homogenized, the reason they use that word is because it is a homogeneous mixture at that point. So milk, in the normal sense, though, you should consider homogeneous. I realize I used the curdled example, but typically if you see this on a test, they're giving you normal milk, not curdled milk. All right, so now we've kind of looked at some different ways we classify matter. We contrasted elements and compounds, and then pure substances versus mixtures, and then the two different types of mixtures here, and you might have to classify those. But now we want to talk about some of the properties of matter and how we classify some of these properties. All right, so now we want to talk about two different classes of properties, which are things that describe matter, and it's going to be chemical properties versus physical properties. And if you have some sort of change going on associated with a chemical property, we'll call it a chemical change. And same thing over here with physical change related to a physical property. Now, it turns out the big difference between these two different types of properties or changes, let's deal with the change specifically. If the change converts one substance into a different substance, we're going to refer to that as a chemical change. However, if whatever change is going on does not convert one substance into a different substance, then it's just going to be a physical change. So for example, if I take the study guide here, and I tear it in half. So turns out paper here is made of cellulose, and the paper that I've got here is still made of cellulose. So I haven't turned one substance into a different substance. It's still the same substance. Tearing the paper would be considered a physical change. And if we look here, this isn't exactly cellulose, but it turns out cellulose is made up of glucose, so I'm going to kind of model it as glucose. And when I tear it, it's still cellulose. So glucose is in this case. I haven't turned it into a different substance, just have two pieces of it now instead of one bigger piece. Okay. However, if I took that same study guide and I lit it on fire, things would be a little bit different then instead. And it turns out when you light it on fire, you convert it into CO2 and H2O. So we'll learn how to balance these reactions later, but I just want to show you that we're turning one substance into different substances, and that's why burning it would be a chemical change rather than a physical change. And so the chemistry term we might use we might use the word burning, but you might also hear the word combustion used. And combustion is a chemical change, but every chemical change often has typically has a property associated with it, and the property associated with it here would be called flammability. And so here we have a chemical change and a chemical property. All right, so other examples of physical changes, and definitely much more likely to see some of these than tearing a piece of paper, are things associated with phase changes. We talk about the different phases of matter, solid, liquid, and gas, and it turns out they can change back and forth. Like when you go from liquid to solid, you're freezing something, and when you're going from solid to liquid, you're melting that something and stuff like that. But it turns out you're not converting one substance into a different substance. So like if we just talk about melting something, like let's say we're melting some ice, well, the way we describe that is we would take water that's a solid and convert it into water that's a liquid. So we often will take the particular phase of matter and write it in parentheses right after the formula for a substance to identify which phase it was in. And so here we just got water that's a solid phase going to water in the liquid phase, but it's water, it's H2O, it's the exact same substance, the exact same compound in this case, both before and after we melt it. And that's why melting is just a physical change. We haven't converted one substance into a different substance. Cool, and it turns out that the property associated with this change we might call the melting point. And in the case of water, it turns out there's a characteristic temperature at which a substance is going to melt. And for water, that's 0 degrees Celsius or 32 degrees Fahrenheit. You'll find out that we're probably going to use Celsius a lot more in this particular class. And so 0 degrees Celsius, that's the temperature at which water melts. Now, different substances are all going to melt at different temperatures, but it is a characteristic physical property of a substance is its melting point. Another example would be like its boiling point, things of this sort. All right, if we look at some other examples that you might encounter somewhere along the way, you might have like a nail rusting. A nail rusting. Now, a nail is made of iron, and when it rusts, it's actually combining with oxygen to form a new compound, iron oxide. And again, we'll worry about balancing these later on in chapter 3. For now, just realize that you started off with 2 different elemental substances and made a new compound. And so you turned one set of substances into a different substance. That's definitely a chemical change. So, and it turns out when a nail rusts, it actually is undergoing oxidation. Not a word you need to know now, but I just want to point out that the property associated with this chemical change might be called oxidizability, things of this sort. So oftentimes, again, these chemical changes will have a chemical property associated with them. Cool. One last one you probably want to be familiar with, and that's dissolving salt in water. And I just want you to think about this for a sec. When you dissolve salt in water, is that a chemical change or is that a physical change? And I asked this one on purpose because it is a little bit tricky. So there's a temptation to think that, oh, I can see what salt looks like, and when you put it in water, it looks totally different. So that must be a chemical change. It must be converting into a different property or a different substance. But it's totally not true. If it turns out if you dissolve salt in water, you still have salt in there. And if you evaporate off the water, your salt's still there. So you'll find it sitting on the bottom of your container. And so it turns out that dissolving salt in water, we might represent it like so. NaCl solid turning into NaCl aqueous. Now, it turns out aqueous here, AQ is the abbreviation for that. AQ just means that something is dissolved in water. But notice it was NaCl, a compound beforehand, and it's still NaCl after you dissolve it as well. We haven't converted it into a different substance, and therefore it's not a chemical change, it's just a physical change. And that's definitely one that's common to show up on your exam in this section. Cool, that's your big difference between chemical changes and physical changes, and chemical properties and physical properties, and these are the most common examples you're likely to encounter. All right, last piece of vocabulary we got for this lesson is just contrasting 2 other classifications for properties. So an intensive property versus an extensive property. So, and your big difference here is really, does the size of the sample matter? So does size matter? So for an intensive property, the size of your sample will not affect it whatsoever. For an extensive property, the size of your sample will totally affect it. So if we look at some examples of this, so your melting point that we alluded to just a second ago, we said that for water, the melting point was 0 degrees Celsius. And notice we didn't say, well, if it's a glass of water, it's 0, but if it's a whole swimming pool full of water, it's going to be some other number. No, the melting point is the exact same temperature regardless of the size of water sample you have. And so the melting point, and typically your phase change points in general, are good examples of intensive properties. Now, on the other hand, for an extensive property, you might have mass. So you put a glass of water on a scale versus putting an entire swimming pool of water on a scale, and those scales are going to read something very different. The mass is going to be very different between those two lovely samples. So the size of the sample is totally going to affect the mass of that substance. Same thing with volume. So the volume of a glass of water is much smaller than the volume of an entire swimming pool full of water. And so the size of your sample is going to totally affect the volume of that sample. So good classic examples of extensive properties. So we'll get a little tricky here now. So it turns out that density is going to be an example of an intensive property. And what makes that tricky is based on the definition. It turns out that density, we'll talk about this more at the end of this chapter, is equal to mass divided by volume. And so mass is an extensive property. Volume is an extensive property, but if you divide one by the other, you get an intensive property of density. And you should definitely know that density is intensive. It turns out that the density of water at room temperature is about 1 gram per milliliter. It's almost exactly 1 gram per milliliter. And it doesn't matter if you have a whole swimming pool full of water or just a glass of water, the density is still 1 gram per milliliter. It is not affected by the size of the sample. Another good example of an intensive property that you should probably know is temperature. So if I've got a glass of water that's been sitting outside all day and a swimming pool full of water that's been sitting outside all day, and they've acclimated to the outside temperature, they've reached thermal equilibrium, we might say. So, well, then they're going to have the same temperature. It doesn't matter that one's a smaller sample size and one's a bigger sample size or something like that. So temperature also does not care about the sample size. It is an intensive property. Now, if you found this lesson helpful and you want to be notified every time I post another one, then you should subscribe to the channel and click that bell notification. You'll be notified as soon as I post a new lesson. However, if you want to make sure that none of your compadres in your class get notified about my lessons or even ever hear about my lessons, that way you get to be the one throwing the curve, then do not like this video and do not share it at all.